Hello, so today I'm going to be doing some problems from section 3.7, and in section 3.7 we learned about implicit functions and implicit differentiation. So before I start that, I just want to do a little quick review about taking derivatives. So we know, for instance, if we have something like this term x cubed, if I want to take the derivative of that term, in other words, I'm going to take the derivative with respect to x of that term, then I get, using my power rule, 3x squared. Then we learned, the next thing we learned is, what if I had something like x minus 4, let me make that 2x minus 4 cubed. And if I wanted to find the derivative of that, again with respect to x, we learned that we needed to use the chain rule because this term isn't simply an x term raised to a power. Rather, it's a function, something other than just x raised to a power. So the chain rule tells me that I first apply the power rule, 3 times the term that is being raised to that power, and then 3 minus 1 is 2. But now I have to deal with the fact that this expression right here is not just x. It's a function that uses x, and I have to find the derivative of that term and use that as well here. So next, in other words, I need to multiply by the derivative of 2x minus 4. So in the end, because of the chain rule and because I'm taking the derivative with respect to x and not with respect to 2x minus 4, I end up with 3 times 2x minus 4 squared, and then multiply that by the derivative of 2x minus 4, which is simply 2. So simplify gives me 6 times 2x minus 4 squared. Okay, now I want to demonstrate how this implicit differentiation is really just an extension of this chain rule. Because now, let's look at this case where I have y cubed. Well, if I want to find the derivative of that with respect to x, then I see that just like with the chain rule here, the term or the expression that I'm raising to the third power is not simply an x, it's something other than x. In this case here, the term was 2x minus 4. In this case, that expression that's being raised to the third power is y. So just like I did before, I'm first going to apply the power rule, and that gives me 3y squared. But now I also am going to need to take the derivative of y, just like I needed to take the derivative of 2x minus 4. And so I'm going to go back here and write that as y prime, just like here. I wrote it as 2x minus 4 prime, using that same idea, right? So I took and applied the power rule to the original expression, and then I realized that, well, since that original expression was not just a simple x, I also have to multiply by the derivative of that inside expression. And so now when I do this, this becomes 3y squared. And what is the derivative of y? Well, the derivative of y is simply dy dx. It's the derivative of y with respect to x. So I end up with, when I take the derivative with respect to x of y cubed, I get 3y squared dy dx. Okay, now let's use that idea moving forward. And so I'm going to first do problem number 3 from section 3.7. And I am asked to find dy dx given the fact that x squared plus xy minus y cubed is equal to x times y squared. Okay, and so I will start by saying, okay, that means that I need to take the derivative of both sides of that equation in order to find dy dx. Okay, so I'm going to do that now. And the first term I have here is x squared. X squared is a simple x term, so it's easy for me to take the derivative of that. It gives me 2x. Then the next term I have is this xy term. So that's going to require me to use the product rule. So the product rule tells me that I would take, let me just get a different color pen for this. Tells me that I would take x prime multiplied by y and add that to x multiplied by y prime. So that's that term there. Then the next term that I have is y cubed. And so like I just saw in the last page that I was working on, so I have minus, because of the net minus here, y cubed, and we just saw y cubed is actually 3y squared multiplied by the derivative of y. And then I didn't leave myself very much room here, so there's a really cool trick I can do here. I'm just going to move that over a little bit so that I can get the room I need. So now I can say that is all equal to the derivative of the other side of the equation. The other side of the equation is x times y squared. So again, I'm going to need the product rule. The product rule tells me that I have x prime y squared plus x y squared prime. Okay, so let's go down now and work through all these derivatives that I need to take and see what I can clear up here. I'll put that in parentheses so that I know that's what I'm taking the derivative of. Okay, now so I have 2x plus, the derivative of x is just 1, so that would be plus y, and then plus x, and the derivative of y is dy dx. And subtract from that 3y squared, again the derivative of y is dy dx, equals, the derivative of x is just 1, so that leaves me with y squared plus x, and now I need to take the derivative of y squared. The derivative of y squared would then be 2y times the derivative of y, which is dy dx. Okay, all right, so it looks pretty ugly, but I do have everything in terms of, I have x terms, I have y terms, I have dy dx terms, y squared terms, kind of a mess. Let's think about what our ultimate goal is and how we can rearrange these terms to make some sense out of them. And remember, our ultimate goal is to get dy dx. So I'm going to start by pulling all of the terms together that are dy dx terms. So I have a dy dx term here, here, and here. Right? So let me rewrite the expression so that I have dy dx, and I have it times x. Then I have dy dx 3y squared. And then if I subtract this term from both sides, I would also have minus, oops, let me change back to my pencil, minus dy dx times xy. Actually, it would be times 2xy. And all of that is equal to, and I'm going to have all the terms that do not have xy on the right. So I see starting on the right already, I have this y squared term. So y squared. And then over on this left side, I have the 2x. So I'll subtract 2x from both sides. And I also see I have this plus y over here, so I'll subtract y from both sides. And I'll end up with that y squared minus 2x minus y on the right. Okay, now I'm going to factor out the dy dx term. So this dy dx times x minus 3y squared minus 2xy is equal to y squared minus 2x minus y. Now I can get dy dx by itself just by dividing by this entire term here. And so that leaves me with dy dx is equal to y squared minus 2x minus y all over x minus 3y squared minus 2xy. And now I'm done. Now I have the derivative of y with respect to x is equal to this expression over here on the right. And like was mentioned in the presentation video, now if I knew a particular x coordinate, I could find the y coordinate that goes with that on the curve, and I could find the slope of the tangent of the line at that point. All right, so now let's try another example. Let's look at problem number 15 from section 3.7. All right, and in this one, we're told that the sine of xy equals 2x plus 5. And so I'm going to start by taking the derivative of both sides. And when I do that, so let me, I guess, write that in here. So I'm going to take dx of the sine of xy, and that is equal to dx of 2x plus 5. Okay. All right, so looks like I've got some chain rule stuff going on here because I'm taking the sine of xy, not just the sine of x. So the first thing that I need to do is take the derivative of the sine is the cosine. So this gives me cosine xy multiplied by xy prime because of the chain rule is equal to, and over here the derivative of 2x plus 5 is simply 2. Okay, so now I'm going to continue on. So this gives me the cosine of xy times, all right, now I see in order to take the derivative of xy, I need to use the product rule, so I'm going to write that out here. And maybe I'll write that out with a different color. So this will give me x prime y plus xy prime. Okay. And all of that equals 2. So I'll go through again, clean it up a little bit more. So the cosine xy times x prime is just 1 times y plus x, and y prime we know is dy dx equals 2. Now I need to do a little bit of, well, my goal is to get dy dx by itself. And the dy dx is inside of this parenthetical statement. So the first thing that I'm actually going to do is I'm going to divide both sides by cosine of xy. So that would leave me with y plus x dy dx is equal to 2 over cosine xy. Now the next thing I'm going to do is subtract the y from both sides. So I have x dy dx equals 2. Oh, that's actually a numerator of a fraction, equals 2 over cosine xy minus y. And now I'm going to divide both sides by x, which gives me dy dx is equal to 2 over cosine xy minus y, that whole thing divided by x. And I can leave it just like that, or I can move it around a little bit. I could combine these two terms in the numerator if I multiply, let me get a different color. If I multiply this y by cosine xy over cosine xy, then I can subtract the one term from the other. So then I would end up with dy dx is equal to 2 minus y cosine xy all over cosine xy all over x, which it can just be simplified to 2 minus y cosine xy divided by x cosine xy. Now, I would have been fine if you would have left it back here at this step before we multiplied in this cosine xy over cosine xy to find the common denominator and combine the fractions. So this right here, let me just kind of box it in red. This right here was fine for me, but I don't think that's the answer they gave in the book. And so you need to do a little bit of algebraic manipulation to get to that answer, which I think is the one they gave in the book. Okay, next I want to do problem number 21. So 3.7 number 21 is sine AY plus cosine BX equals XY. And in this problem, we're told that A and B are constants. And so again, we're being asked to find dy dx. And so the first thing I'm going to do here is look at this first term, of course, which is sine of AY. And I am going to need to use the chain rule because I'm not taking the sine of a constant multiplied by x. Instead, it's AY. So the derivative of the sine is the cosine. So I have the cosine AY. And then I have to multiply that by, of course, and I have been changing my color, so let me stick with that. Multiplying that by a y prime, okay? Then I come over here and again, I do have to take and use the chain rule again because this term isn't simply an x term, it's x being multiplied by a constant. And so that gives me a negative sign because the derivative of the cosine is negative sine bx multiplied by, and we'll just go ahead and put it here, the derivative of b times x, okay? I'm just writing out all the little steps so that we're not going to be confused. And then this is multiplied to take the derivative of this last term. I'm going to need to use the product rule, which we've seen now a few times, but again, I'll still write it out. So that would be, and I think I've been using this other color to write that out, so let me do that. The product rule would tell me that I have x, y prime, sorry, x prime y plus x, y prime. Okay, so now let's go through and take some of these derivatives. And change to black. That gives me that the cosine of ay multiplied by, and when I take this derivative ay prime, the a stays, and y prime is dy dx. And then plus the minus here, so it's minus sine bx. And then the derivative of bx is simply b equal to, the derivative of x is 1, and so that gives me y plus x, and the derivative of y is dy dx. Okay, again, my goal is to get dy dx by itself, so I am going to put the dy dx terms on the left. And so I have this term here already. I have this term on the right side of the equation, so I'll have to subtract that term from both sides. And I will get cosine ay a dy dx, and subtract the negative x dy dx from both sides. And then I want everything that doesn't have the dy dx on the right-hand side. I already have the y there. And on the left, I currently have this sine bx times b being subtracted. So I'm going to have to add that to both sides. So that gives me sine bxb. Okay. Now I can factor out the dy dx, the terms on the left, and that would give me dy dx multiplied by, and I'm just going to change the order. Instead of saying cosine ay, I'm going to say, and being multiplied by a, I'm going to put the a in the front because we usually do put the constants in the front. So I say a cosine ay minus x equals y plus, and again here I'm going to move this b to the front, b sine bx. And then finally, I just need to divide both sides by this parenthetical, and that will give me the fact that dy dx is equal to y plus b sine bx, whole thing divided by a cosine ay minus x. And that's the end. Okay, so I hope these examples have helped. Like always, if you have any questions,